Hi, so let's begin. Welcome to today's lecture. Let me introduce the speaker, Manuel Engel. Manuel is a true native in VASP. He first contributed to VASP around 7 years ago, and he joined the company right after his PhD in Georg Kress's group at the University of Vienna. His main expertise lies in phonon calculations, binarization, and he has a bit of a knack for useful gadgets, like the VS Code plugin to quickly access the documentation for Inca flags. And well, you can do some more things. Maybe you can check it out if you have time. Today, he will present an overview over the different features to compute phonon properties. Manuel, please take it away.
Thank you, Marie-Therese, for the lovely introduction. As Marie-Therese already said, I'm going to talk about phonons today. And in particular, I want to talk about phonons in the harmonic approximation and how you can use VASP to calculate those vibrational properties of your material. Now, the talk is structured as follows. First, I will talk a little bit about the response of a system to an external perturbation and how that leads to the definition of the interatomic force constants, which is very tightly interwoven with the vibrational frequencies and the eigenmodes of your system. In VASP, we can use a supercell-based approach to calculate those phonon frequencies everywhere in the first Brillouin zone, and I will show you how that is done. Then I will go into the more nitty-gritty of the practical aspects of calculating the force constants from either finite differences or density functional perturbation theory. Afterwards, I talk a little bit about external tools that you can use to complement VASP in either calculating phonon frequencies or to help analyze the phonons afterwards. Finally, I'm going to talk about a very interesting subject, namely phonons in polar materials, where the emergence of long-range electrostatic interactions has a profound effect on the phonon dispersion relation. This leads to a phenomenon known as LOTO splitting, and I will show you also how to perform these kinds of calculations in VASP and what to take into consideration. So this journey begins, as so many others do, with the cone-sham equations. Here you have your usual Hamiltonian, the cone-sham Hamiltonian, the cone-sham orbitals psi and k, and also the eigenvalues E and k. In this particular case, I also write an overlap operator S, which takes care of non-orthogonal orbitals. In VASP, we use the projector augmented wave method, which does have non-orthogonal orbitals. And if you want to solve this equation for a ground state equilibrium calculation, you usually just take your first guess for your orbitals. Then you can construct the density based on those orbitals. You can construct an effective potential. And finally, you have an expression for the total energy, which you want to minimize. And so you iterate this equation self-consistently and end up with a particular set of solutions. The question that now is raised is what happens if you introduce a perturbation to this equilibrium system? For example, you can displace an atom from its equilibrium position. This changes effectively your external potential in this expression for your effective potential. And you can solve these equations again, which gives you some response to this perturbation. And fortunately, these linear response properties are all accessible from the ground state. Linear in this context just means that the response your system has to a perturbation is proportional to the strength of that perturbation. And so I'm going to look at 3 different kinds of perturbation that we can apply to the system. So the first one I already said is going to be an atomic displacement. You can pick any number of atoms in your crystal lattice and you just shift them by a small amount. Here we use the index M for this atomic displacement to just be a compound index labeling the atom index capital I and a Cartesian index alpha. The other possible perturbations that I'm going to look at are a homogeneous strain. So by either squeezing the lattice or stretching it, it will introduce some kind of stress response that tries to bring the entire crystal back to its equilibrium configuration. And finally, we can also apply a static electric field that may polarize your crystal. If you write the total energy as a Taylor expansion of these three types of perturbations, at first order, you will get three terms, one for each kind of perturbation. The first one, with respect to the atomic displacement, is going to be a net force. The one that pertains to the electric field will give you a polarization. And finally, the strain will give you some stress. At second order, you will get 6 terms, because there will be 3 double derivative terms and 3 mixed derivative terms. And of course, the higher you go, the more terms there will be. At second order, all of these 6 tensors have some kind of physical meaning. So here they are written out. For example, the second derivative of the total energy with respect to the strain will give you the elastic moduli. However, in the context of this talk, we talk about phonons, only 3 of those are going to be relevant. These are the dielectric susceptibility, which is related to the dielectric tensor, which I will show later, the Born effective charges, and the matrix of interatomic force constants. Now, for now, I will only focus on the later, so the matrix of interatomic force constants, and the other 2 are then brought into the picture when we talk about phonons in polar materials. So now I'm going to talk about how these force constants can lead to phonons, so to lead to the vibrational properties of your material, and how you can in principle calculate those force constants. So once again, we write the total energy as a Taylor expansion in terms of the atomic displacements. Here, this atomic displacement is written in terms of a nuclear coordinate Ri alpha, which is the displaced coordinate, and in terms of the equilibrium positions R0. And at first order, you will obtain forces. This is just a force that tries to bring the atom back to its equilibrium position. However, since we evaluate this force in the equilibrium configuration, it is going to be 0 by definition, which leaves only the second order term to contribute to the energy change up to second order. And we will stay at second order within the harmonic approximation. In general, of course, higher order terms can play a role. There are materials where anharmonic contributions play a big role, but that is beyond the current capabilities of this phonon code in VASP. So I will focus solely on harmonic contributions. And so here we do one final variable transformation where we go from this difference between nuclear coordinates to just a displacement vector, where once again, the capital I is an atom index and the alpha means the Cartesian index in the 3 spatial directions. And so this energy change is simply just a multiplication of these force constants with the displacements of the ions. Now we can write down the Hamiltonian for such a coupled system of atoms. This is simply a 3-dimensional, more complicated version of a harmonic oscillator. All the atoms are coupled with spring constants. So in some sense, the force constant matrix is simply a generalization of the spring constant to 3-dimension for lattices or for 3-dimensional systems of atoms. And we can write down from this the equation of motion, and we know in principle how to solve such an equation of motion. So we can just make an ansatz in terms of a traveling plane wave. You see here that the solution, which is the atomic displacement, that is now labeled by an additional index nu, which just labels all the different solutions to this equation. It is a prefactor, which is 1 over the ionic mass, or the square root over the ionic mass of that atom. And it has a vector E, I alpha nu. This is, in some sense, a direction vector that tells you in which direction the atom is going to oscillate in this wave. And this direction is then modulated by a phase, which oscillates with a frequency omega nu over time. And so once you substitute this back into the equation of motion, you arrive at an eigenvalue equation with the very important dynamical matrix that needs to be diagonalized. This dynamical matrix, as written here, is simply a rescaled version of the force constants. You see here on the right that it is essentially a force constant matrix, but divided by the ionic masses. And once you diagonalize this dynamical matrix, you obtain the vibrational frequencies, the angular frequencies squared, to be precise. And as eigenvectors, you get these direction vectors. And we can interpret these vibrations as a collective excitement of the crystal lattice. And so we attribute to them a quasi-particle that we call the phonon. So these omega nu, we just call the phonon frequencies. And these direction vectors, complex direction vectors, we call the phonon eigenvectors or phonon modes, as they give you exactly the way the atoms move during this wave. However, there's a bit of an issue with this picture, a practical issue, if you will. The number of solutions you obtain from this diagonalization is equal to the total number of degrees of freedom in your system. So if you have a supercell, the number of atoms multiplied by 3, because there's 3 spatial directions, will give you the number of solutions. And so if you keep increasing this supercell and maybe even go to the limit of an infinite crystal, you will end up with infinitely many solutions, which is hard to keep track of. And so we would like to reformulate this equation in terms of the primitive cell only. And to do this, we rewrite our nuclear coordinate R capital I in terms of a position of a unit cell plus the position of an atom within that unit cell. You can do that in a periodic crystal where all the unit cells are periodic images of one another. So this index L is essentially just a unit cell index, and the index lowercase I is now the atom index within that unit cell. And so you rewrite your force constants in terms of these new indices, lower L, lowercase I, alpha, and then also for the other atom. Using the periodic, so the translational invariance of this quantity, we can perform a Fourier transformation from real space, from this picture of force constants between atoms, to reciprocal space, where we can define our dynamical matrix now with only the unit cell indices, lowercase I and j, for a particular wave vector q. We call this the phonon wave vector. And in case of a finite supercell, where let's say you have a 4x4x4 supercell, you will also end up with exactly 4x4x4 q points for which this equation will be exact. And you can once again diagonalize this dynamical matrix that is now written in terms of the unit cell, and you will obtain phonon frequencies and eigenvectors, just as before. However, this time the number of solutions is fixed by the number of atoms in the unit cell. So if you have 2 atoms in your unit cell, then that's 2 times 3, 6 possible phonon branches, we call them. However, you now get solutions at different wave vectors q as well. And so if you increase your supercell size ad infinitum, you will eventually get a continuum of q vectors. This is very similar to how the Kohn-Sham equations work in reciprocal space, where you sample all of your first Brillouin zone with k vectors and obtain bands at those points. And so in practice, what we can do is to interpolate to different q vectors. If our force constant matrix is well behaved, meaning that it is large enough so that the difference between different atoms that are large, that are far away in real space becomes negligible, then we can interpolate this to various different q points at arbitrary points with Fourier interpolation. And this is the basic idea behind how you calculate the phonon dispersion relation, meaning your phonon frequencies as a function of the q vector in VASP. And so now I just want to highlight what such a phonon could look like. I chose here one particular q vector. On the left, I show a part of this dispersion relation. I show the 3 lowest frequency branches. They're called acoustic branches. And for this particular q vector, I also plot the modes, the vibrational modes. And here in this image, the phonon wave vector goes from left to right, and I show a top view and a side view of a monolayer structure, MoS2. And the first mode, the lowest frequency mode for nu equal 1, is a wave that is longitudinal. It goes from left to right, and all the atoms also vibrate or oscillate on a left to right motion. The second branch is a transverse mode that happens in plane of this monolayer MoS2 structure. So you see at the bottom layer that there is no movement out of plane visible. And finally, the last branch is also a transverse mode, but this time the vibrational motion happens out of plane of this monolayer. So now we can calculate the phonon dispersion using a large supercell and Fourier interpolation. All we need for that is the force constant matrix. I will tell you in the next section how you can compute that in practice. And we need the force constants to be situated in a large enough supercell so that Fourier interpolation becomes possible. You have to do convergence tests, of course, to make sure that is okay. And it might not even be possible in practice sometimes. So there are some limitations to this method. And as a last word, I mean, all of you probably know this already, but phonons are very important. They're ubiquitous in material science. They pop up everywhere from spectroscopy to superconductivity and electrical conductivity, thermal transport, zero-point renormalization, which is something I've worked on for a very long time, meaning that even at 0 Kelvin, the quantum fluctuations of the crystal lattice contribute to the electronic band structure. And you can also get the sound velocity of your material from the phonon dispersion relation. So you can go to the long wavelength regime, which is just around the gamma point, and get the slope of this particular branch, which gives you the sound velocity in this direction. So now I will get more into the practical details of how to calculate the force constants using either the finite difference approach or the density functional perturbation theory based approach. We start with finite differences, where the idea is very simple. In VASP, you can activate this approach by setting iBrian in the InCar file to either 5 or 6. I will get to the difference in a second. And you displace one at a time individual atoms by a small amount. So in this case, you displace the ion j in the direction beta by a finite amount, lambda. And then you can calculate the forces that this change incurs. You can calculate the forces on this atom, on the other atoms. And to get the force constant matrix, you essentially just displace an atom in a positive direction, get the total force, displace the atom in the other direction, get the force, and then take a central difference between the two, which gives you your force constant matrix. There is a bit more freedom to this. If you set n free in the InCar file, you can control how many displacements are being made. The default n free equals 2 gives you a simple central difference formula, which is good for most cases. You can, however, also do a first order finite difference with a higher accuracy stencil, which is what n free equals 4 does. It requires 4 displacements to do this difference. And finally, you can also set n free equals 1, which gives you a simple forward difference, requiring only a single displacement. The amount of displacement measured in angstrom can be set by the POTIM tag. The default is 0.015, which is good in most cases. And finally, there is a difference between iBrian 5 and 6, and that is just symmetry. For iBrian 5, you displace all the atoms of your crystal, one after the other. And for iBrian 6, symmetry operations are applied, and only a subset of these displacements is needed. So in practice, you always want to use iBrian 6, essentially. There should never be a reason to use iBrian 5, unless you are in a very, very specific scenario where you want to displace all the atoms. Now, the finite difference approach has a huge advantage, namely that it works with practically any density functional. That means the basic LDA, GGA functionals, but also meta GGA, DFT plus U, van der Waals functionals, hybrids, and even the random phase approximation. Here I just summarize some quick tips or things to look out for when you perform these calculations. The first is to use prac equals accurate, which one of the things it does is it increases the density of your FFT mesh compared to the default, which is prac equals normal, if I'm not mistaken. This reduces the so-called egg box effect. It's when you want to describe function, a potential in this case, on an FFT grid or any grid, and you move the potential by a small amount, then the integration of this potential can change based on the sampling density of your grid, because the grid points might not align anymore. And so by increasing the sampling density of your FFT mesh this way, it reduces this egg box effect, which reduces numerical inaccuracies. There's also a tag called addGrid, which increases the FFT meshes of certain particular meshes, but in this case, it does not really help with the phonon convergence or accuracy. It instead increases the computational demand by quite a bit. So I advise against using it unless it is what you really need. When you do these calculations, you want to converge your phonon frequencies, and one way to do that is to look at the highest frequency, the highest optical frequency of your phonons at the gamma point, and you try to increase the electronic cutoff energy, E and cut, and also the density of your K-point mesh until you reach convergence. Another thing to watch out for is, of course, the POT-IM tag, which sets the amount of displacement for the atoms, which you want to keep in a certain region. I will get back to this in just a second. And finally, since we do supercell calculations for interpolating the phonon modes, you also want to increase the supercell size and try to converge with respect to the supercell. In this case, when you keep increasing the supercell size, you should in principle be able to, at the same time, reduce the number of K-points that you need. Because a supercell calculation in a 4x4x4 supercell should in principle give you the same results as a unit cell calculation with 4x4x4 K-points. But here we need the supercell. So increasing the supercell size means you can usually reduce the number of K-points. Here's a nice table at the slide, which illustrates this for a very nice symmetric example. And so now, after discussing the finite difference approach, I will move on to the density functional theory, density functional perturbation theory approach, where instead of doing an explicit displacement of the atoms one by one, we instead take the Kohn-Sham equations and analytically calculate a derivative with respect to an atomic displacement. If you do this, you end up with this Sternheimer equation, which you can solve, and you end up with a set of perturbed orbitals, or a set of these orbital derivatives from which you can estimate your response by adding it to the ground state solution. And from this, you can once again calculate forces. Here, the force constants are calculated in VASP using a central difference formula again, based on a plus and minus displacement. And yeah, the DFPT approach has some disadvantages. Not in principle, but in VASP, the implementation of the DFPT driver only computes the phonons for q equals 0. In principle, DFPT can be formulated to calculate phonons for any arbitrary q with high accuracy, but the implementation in VASP only allows phonons to be calculated at the gamma point. Another disadvantage is that it does not out of the gate work for most density functionals, and so only a subset of density functionals is available for DFPT. There are also a few positions where still finite differences are used. One is the second derivative of the exchange correlation functional, and the other one is the one we've just seen, which is the calculation of the force constants in terms of a central difference. And yes, as I've mentioned, only the local, semi-local functionals, the basic LDA, GGA functionals are supported for this kind of driver. And because of these limitations that are present currently in VASP, I recommend to use the finite difference driver over the DFPT driver for most scenarios. So once you run such a finite difference calculation, the OUTCAR, the output that comes to the standard out, will give you some additional information. First of all, it reports the number of degrees of freedom that the system has, that it has chosen, in fact, which depends on the number of atoms in the unit cell, the applicable symmetries and all this, and also reports the number of displacements that it does, which is essentially dependent on the n free you have set. It reports the forces for each step in the OUTCAR file, which is also something you can check for convergence to see if your structure is well optimized. And it finally writes also the force constants to the output files, the XML and the HDF5 file. Of course, I recommend to everyone to use the HDF5 file due to its better storage and access properties. And by default, if you set iBrian equals 6, for example, the dynamical matrix is also constructed for the gamma point from the supercell force constants and diagonalized, which is not the phonon interpolation that I was talking about, but it is simply taking all the degrees of freedom of the supercell and giving you frequencies and eigenvectors for those. But those are only available at the gamma point for the supercell. So I want to highlight some of the things I've just mentioned with regards to convergence. I want to highlight them on a practical example. Here I pick silicon, where I show a convergence of your phonon calculation with respect to the electronic cutoff, EN cut, and also to the k-point mesh in the k-points file. And you see that for this particular case, you already get reasonable results for an 8x8x8 k-point mesh in the unit cell, and an electronic cutoff of 245, which is the default for this particular pseudopotential, gives you reasonable results. You can increase these to get even higher accuracy. And in general, you want to test as much as possible that you have actually reached convergence. Here, I also show that setting this add grid tag that I mentioned before doesn't actually improve the accuracy in this particular case. So avoiding it gives you a better computational performance in comparison. The other thing I want to highlight is this potim tag, which sets the amount of displacement, so the step size in a sense for the finite difference driver. And we can compare that. So we can compare different finite difference calculations at various different potim settings against the DFPT driver, which works analytically. Of course, there's no finite displacements at this initial step. And as you can see, there is a region where the finite difference and the DFPT driver are in pretty good agreement. And the scale on the left for the frequencies is a rather narrow window. So the precision here is already relatively high, but you can see that there are two regimes. One where the displacement becomes too small and you run into numerical issues, numerical noise, meaning that you divide a small number by a small number and that can give you nonsensical results at a certain point. Or your displacement step is too large and you start to get contributions also from higher orders, because you do not approximate a linear regime anymore, but you approximate something else with the finite difference. So you want to make sure, as a part of your convergence test, that the chosen potim actually falls inside this region where the results are reasonable. The default is pretty good for most cases, but make sure to always do your own testing. So now I will get to the most interesting part, the new part actually in newer versions of VASP, which is available as of VASP 6.3.2, and that is the interpolation of the phonon dispersion relation. You can activate this in the INCAR file by setting lphone dispersion equal true, and you have to supply a q-points file, which has the same format as a k-points file, and it contains the q-points at which you want to calculate the phonon frequencies and eigenvectors. So you start the calculation by calculating the force constants, as I have shown, by either using iBrian 6 or iBrian 5, 7, and 8. However, the last three are only available as of the most recent version of VASP due to a bug. You can also choose to use the force constants that were already calculated in a previous calculation by renaming the VASP out H5 file into a VASP in H5 file and specifying lphone read force constants equals true, which might take the cake as the longest INCAR tag. Finally, the phonon frequencies are written to the OUTCAR file and also to the binary VASP out H5 file, and you can get an interpolation of your phonon band structure. Here I show the issue with converging with the supercell size. So this is an overlaid plot for different supercell sizes going from 111 all the way up to 666. And for a 111 supercell, which is just the unit cell, the results are pretty much nonsensical. There's some resemblance of a phonon band structure, but it is completely wrong. And then only with a 4x4x4 cell do you get into the region of convergence, where your results are relatively accurate. Yeah, once again, I say here that the K-point sampling can be reduced as you keep increasing the supercell size. And well, obviously, the larger the supercell, the more expensive it is. So if you end up with a single K-point at some point, you can use the gamma-only version of VASP to reduce your computational cost even more. Just as a highlight, I show that you can use different density functionals here for the finite difference driver and interpolating the phonon dispersion relation, which can be quite important for certain areas or certain materials. Here I compare the standard BBE potential that comes for silicon against the R2 scan and the AGC Sol functionals. And there's quite a bit of difference between those two more complex functionals and the standard PBE. If you do these kinds of calculations, make sure that you relax your structure. So do a geometry optimization with the functional that you want to use also in the supercell calculation. Make sure, of course, that your system is converged with E and cut and K points as always. And keep in mind that for complex functionals, the supercell calculations become even more demanding. I'm moving on to yet another example. This time I go back to this monolayer MoS2 structure that I showed earlier. And I show a calculation that comes from a 6x6x1 supercell at the gamma point only for the K-point sampling. And in this particular case, I use an Ian cut of 200, and I show the phonon dispersion relation as the code produces it. As you can see at the bottom of the plot, there is a small region close to gamma where the phonon dispersion dips below 0. What this means is that these phonon modes have imaginary frequency. Remember, the eigenvalues of the dynamical matrix are omega squared. So if you get negative eigenvalues, the frequencies themselves become imaginary, which is, of course, an unphysical thing. There is no imaginary frequency here. And on the plot, we simply visualize that as negative frequencies. And sometimes, so I mean, this usually is indicative of some kind of problem with the calculation or maybe with your system. And there's various reasons why that can be the case. The probably simplest explanation is that there is a convergence problem, or your Ian cut might be too low, your lattice parameters might not be optimized properly, your supercell might be too small or too few K points. However, this can also indicate physical instabilities, structural instabilities. For example, in perovskite systems, for example, the vibrational modes can be strongly anharmonic, and so you do not capture those with just harmonic phonon calculations. And there you can encounter imaginary frequencies. You can also encounter imaginary frequencies when you're close to a phase transition as the system becomes unstable. However, in this case, it was just an Ian cut that was too low, and so increasing it to 257 fixes the problem, and you get positive phonon frequencies everywhere. Now I take the opportunity to list some more common pitfalls that you may encounter when you run these kind of supercell calculations. The first one is to always optimize your structure. Preferably, you want to optimize your primitive cell before you construct your supercell with the functional that you want to use. Next, there is a bit of a subtle issue that can sometimes arise when you do calculations in a supercell that is related to the FFT mesh, because the FFT mesh that VASP chooses by default, it can break the translational symmetries of your crystal. Imagine having a 4x4x4 supercell. However, the FFT grid is not divisible by 4 in each direction, which means that the different cells have different kinds of FFT grid points in them. And so the potential is not directly transferable from one to the other without causing some kind of numerical inaccuracy. To prevent that, it is not usually a big issue, but if you run into some kind of issues, this is definitely something you can test. You can try to set your FFT dimensions manually using the ngx, ngy, and ngz in-car tags. Another thing that is kind of important is to choose a supercell that is kind of convenient for these kinds of calculations. So avoid very slanted supercells with very sharp angles. Try to go for something that is more cubic. The reason for that is that because for very slanted supercells, there's one direction where the periodic images of the atoms are very close. And so in that direction, your force constants might not decay fast enough so that they are negligible at large distances. And so you will end up using more atoms for your calculation that would be necessary. Going with a cubic cell or a close to cubic cell instead will require in general less atoms and therefore also runs faster. Yes, I've already mentioned this. For very large supercells, you want to use the gamma-only version where you only require a single K point at the gamma point. This provides a substantial speed up under normal conditions. You want to avoid LREAL equals auto, which activates the so-called real space projection scheme, which usually speeds up calculations in supercells. However, in this case, it can incur inaccuracies when calculating the forces. So I would leave it at the default, the reciprocal space projection scheme. You also should avoid n3 equals 1. Yes, it is a choice, but in my experience, it's usually not the best choice. Also, the EN cut, by default, I can already tell you that you probably need to increase it from the default, maybe by about 30%, since the default is usually not accurate enough to get very accurate forces, which are necessary for these calculations. And there is a little quirk related to the Q points file. Currently, the Q points in this file are specified with respect to the primitive cell that VASP finds during the supercell calculation, which makes it a bit inconvenient to specify. You essentially have to run the supercell calculation once so you just start it as a dry run, you get the primitive cell information, and then you know how to specify your Q points. I'm currently working on a fix that should be available very soon, where you can also specify the unit cell yourself. Now I can take the time to talk a little bit about additional tools that work in tandem with VASP related to phonons. The first one is the well-known package phonopy, which is primarily maintained and developed by Atsushi Togo. Now VASP can, at this point, already calculate the phonon dispersion at arbitrary Q points using these supercell calculations. So phonopy can be used as a post-processing tool, which gives you access to more quantities like the phonon group velocity, thermal properties, and more. However, it can still be used to calculate the phonon dispersion relation for convenience sake, for example, from an already computed force constant matrix by VASP. You can specify with the --FC command line argument that you want to calculate your phonons and read in the force constants from a VASP calculation by specifying this VASP run XML file. However, there's still one reason why you would want to use phonopy. In some cases, it is possible to run individual VASP calculations for individual displacements that can be generated by phonopy, and the number of these displacements might be lower than what VASP finds. Phonopy by default uses more symmetries than VASP, and so the total number of displacements needed might be lower. The second tool that I would like to highlight is the Phonon website, a tool written by my friend and colleague Enrique Miranda. It allows you to upload a calculation, a finished calculation, or the output of that calculation, and analyze the vibrational frequencies and the modes of that calculation. It automatically gives you the phonon dispersion relation, and it allows you to plot these nice pictures, these nice animations of phonon vibrations. In fact, the one of the MOS monolayer I showed you earlier was produced with this Phonon website. The way to use it is you upload your calculation. So for VASP, there's a little Python script which generates a JSON file from the binary output. And for phonopy, you can simply upload this band.yaml file. And then it allows you to pick certain points in this dispersion relation, points in the first Brillouin zone that you want to highlight. And finally, I want to also give a spotlight to our in-house post-processing package, Pi4VASP, not to be confused with P4VASP. Pi4VASP is a Python package that allows you to load a calculation, a VASP calculation. It reads by default the HDF5 file, and it allows you, in this particular case related to phonons, to get direct access to the force constants. It allows you to print them to the console, but it also allows you to plot the phonon dispersion relation or the phonon density of states. Now, the phonon density of states is also something that you can calculate with the new code. I just did not specify here exactly how it works. And now I'm going to go into a physically very interesting topic, phonons in polar materials. In this particular case, the vibrations of the lattice will induce long-range interactions due to electrostatics, due to dipole-dipole interactions that can lead to very, very long-range components of your force constant matrix. And that is a problem because we need to account for all the force constants in our supercell, and we cannot have infinitely long supercells. So to highlight the downfall of this method, in the case of polar materials, I pick a very pathological example, magnesium oxide, which is a strongly polar material. And if I try to calculate the phonon dispersion relation with the code I've described so far, the following thing happens when you try to increase the supercell size. We start with a 2 by 2 by 2 supercell, and then we keep increasing to a 3 by 3 by 3, 4 4 4, 5 5 5, and 6 6 6. And as you and is hopefully evident, there is a convergence problem. These peaks that are the highest optical phonon frequencies, they just keep increasing. And around the gamma point, we have this very sharp dip in the phonon dispersion relation. So evidently there is a convergence problem. And as I've already said, the reason for that is that there are long-range components in the force constants that make it not amenable to Fourier interpolation. And simply increasing the supercell size is probably never going to fix it, even if you go to completely astronomical supercell sizes, because directly around the gamma point, this problem will never be resolved. So what can we do? Well, the phenomenon in principle, we can think about in 1D when you have atoms in a linear chain. And in a polar material, these atoms will have different effective charges, opposite effective charges as you go from left to right. And so displacing some of these atoms in the positive direction and displacing the other atoms in the negative direction can lead to a polarization of your crystal. And this polarization in the long wavelength limit can be a macroscopic effect, because your phonon will essentially just be a very, very long wavelength polarization that moves across your lattice. And if you try to do Fourier interpolation from this force constant matrix that you just obtained from a supercell calculation, you will truncate at values that are still important. And this gives you Gibbs oscillations in your phonon spectrum, which makes it very difficult to converge, if not impossible. To fix this, we can try to separate the long-range behavior from the short-range behavior of the force constants. So on paper, we can simply write the force constant matrix as the sum of a short-range part, which can be Fourier interpolated, and a long-range part, which we have to model analytically. And in this case, the model is that of a dipole-dipole interaction. We can, in principle, also have higher order multipole interactions, but currently only the dipole-dipole interaction is available in VASP. And this analytic model is essentially one part of an Ewald sum, so of a rapidly convergent sum in reciprocal space. It goes over all the reciprocal space lattice vectors G, and it has this final term here, which is just a suppression term that makes this sum rapidly convergent. And it also contains two quantities that we need to supply. The ion-clamped dielectric tensor, which is related directly to the dielectric susceptibility, which I showed earlier, the very beginning of this talk, and the Born effective charges, which is the other second derivative quantity that I showed. And so the question now becomes, how do we calculate those two quantities, and how do we even use this model to correct for these long-range phonons? The two quantities and how to calculate them I will show a bit later. First, I focus on the scheme that we can devise. So the dynamical matrix can also be split in a short-range and a long-range component, just as the force constants can. It's just a Fourier transformation after all. It's a simple linear transformation. And so the short-range dynamical matrix we can obtain by Fourier interpolating the short-range force constants. And the long-range dynamical matrix, once again, can be modeled by this long-range function. The scheme now is the following. we compute the force constants using VASP, using a regular supercell, using DFT, everything I've told you up until this point. Then we remove the long-range behavior from the force constants by subtracting this long-range function. We then Fourier interpolate only the short-range part to the short-range dynamical matrix. This is now well behaved and amenable to Fourier interpolation because it only has the short-range components. And finally, we can add back up the long-range part of the dynamical matrix, given at the particular Q point that we're interested in. And here is the version of this long-range part for the dynamical matrix. It looks slightly different, but that is simply a Fourier transformation of our long-range force constant model. And with this, I mean, all of this is now implemented in VASP. We can calculate phonons also in the presence of long-range electrostatic interactions. Yeah, and now I get back to our example of magnesium oxide, the one that failed before. And in addition, now I set L phone polar to true, which activates the scheme I just showed you. And we supply the ion-clamped dielectric tensor and the Born effective charges by specifying phone dielectric and phone-borne charges. And here I show a before and after scenario of this 2x2x2 calculation. Here is the same picture I showed you earlier where L phone polar equals false, the default. And now I show it with L phone polar equals to true. And there's a huge difference at the gamma point or close to the gamma point. In fact, the frequencies pertaining to these three optical modes split in energy. Two of them are largely unaffected. They stay at the same energy level as they were before, but one of them splits off and becomes much, much higher in energy. And the reason for the splitting, which by the way we term LOTO splitting, LOTO because longitudinal optical and transverse optical, it is because only the longitudinal optical modes couple to this long-range electrostatic field. If you move the atoms in a longitudinal fashion, it produces this long-range behavior in the longitudinal direction, in the travel direction of your phonon. If you do a transverse motion, the phonon does not couple to this. And so only the longitudinal optical modes split off. And now we can do our supercell convergence again. Keep increasing the supercell size to 3x3x3, 4x4, 5x5, and 6x6. And as hopefully evident, it converges rapidly. It converges much faster, and there are no more weird artifacts. And already with a 4x4x4 cell, we obtain a very accurate phonon dispersion relation because of this correction. It is very vital to do this for polar materials, for strongly polar materials. I also highlight another interesting effect that can happen in the presence of these electrostatic interactions. I pick here an example that has a more anisotropic crystal structure, namely aluminum nitride in the Wurzite structure. Wurzite is a layered hexagonal system. So you have a layer, a 2D layer essentially of hexagons that are stacked in a certain order on top of each other. And because there is a difference between the direction in this hexagonal plane and the direction that goes out of plane across the layers, your phonon can polarize the material differently depending on where it travels to. If it travels in plane, the polarization can look different than if it travels out of plane. And so if you do a phonon calculation in such a material with polar interactions enabled, it can happen that your phonon frequency depends on the direction of your phonon wave vector, which is exactly what happens here. There is a splitting. So without LR means without the long-range correction, and with LR means with the long-range correction. So with the long-range correction, you see that there is a splitting, or not a splitting, but a discontinuity in the phonon frequencies around gamma. Some of them just simply stop at the gamma point coming from a certain direction. And this is perfectly physical. The direction dependence is particularly strong around the gamma point because that's where the long wavelengths sit, and where this polar correction is the strongest. At the gamma point directly, the value itself is really meaningless as it depends on the infinitesimal direction of your Q vector. Okay, and now I will go to the final part of this talk, which is talking about how you can calculate the two quantities that you need, namely the ion clamp dielectric tensor and the Born effective charges. And to do this, we once again have two major ways of doing it, either using the response to a finite electric field using the PED approach, which stands for perturbation expansion after discretization. And the other one is again using density functional perturbation theory. You can activate those using the L-calc epsilon or L-epsilon tags respectively. I will first talk about this PED approach, which computes the cone-sham states and the total energy under an applied electric field. This includes an additional term when calculating your total energy, which depends on the polarization of the lattice. And the polarization is given in this modern theory of polarization in terms of a Berry connection. So we can calculate this from our orbitals. And we end up with a Hamiltonian that has this little extra term, which is just the derivative of your polarization with respect to this perturbed function. And it will look something like this, which is a discretized, which uses the discretized notation of your K lattice to take overlaps between neighboring K points. And we can iterate this until self-consistently to obtain these states psi epsilon, the states that you get when you apply an electric field. These S are essentially the overlap matrices between the neighboring K points. I will not go into the detail of how this works exactly. To activate this mode, as I've said, you said L-calc epsilon equals to true. And then you can apply the electric field. You can even tune it by specifying E field PED in each direction. The default is 0.01 electron volt per angstrom. Once you have done this, you can once again obtain the quantity you need through a finite difference formula. In this case, you can calculate the dielectric susceptibility, which directly gives you the dielectric tensor. And in the OUTCAR file, this will be reported as the macroscopic static dielectric tensor. Similarly, you can calculate not through the polarization, but through the forces that occur due to the electric field. The change of the forces due to the electric field, you can calculate the Born effective charges, which is reported as Born effective charges. And then you can supply those quantities, take them from the OUTCAR. There are some scripts available, if I'm not mistaken, that can transform them from the OUTCAR to the INCAR and specify them there. And finally, the other way of computing those quantities is by the use of DFPT once again. But instead of using DFPT with respect to an atomic displacement, we use it to calculate the derivative of our orbital with respect to the K point, with respect to this Bloch vector. This again is a Sternheimer equation, which you can solve. You can even use a finite difference stencil for this using the PED method if in addition you specify LPED equals true. And once the derivative of this orbital has been obtained, you can use it to calculate this polarization vector beta. In principle, if you had norm-conserving pseudopotential, I think it would even be the same quantity, but because in VASP we use the projector augmented wave method, it is a bit more complicated, but I spare you the details of how this actually looks. So in this modified equation here, we obtain the response of this orbital with respect to an electric field by iterating it, and this delta HSCF is the microscopic cell periodic average of the Hamiltonian due to the change in the orbitals. So you obtain, as solutions to the second equation, you obtain the change of the orbitals, or the derivative of the orbitals due to the applied electric field. And you can use this orbital derivative together with your polarization vector to get an expression for the dielectric tensor. Once again, the output is reported similarly to the other case in the OUTCAR file. One particular advantage of this method is that it runs only over occupied states. This sum only needs occupied states to calculate this dielectric tensor, which usually is quite a bit faster. And in order to get the Born effective charges, we can once again use this idea of estimating the perturbation of a particular state by adding our derivative of the wave function with a small finite amount, and we take another finite difference formula to get the change of the forces due to the electric field. Or equivalently, you can think of it also as a change of the polarization if you move an atom. Once again, this is reported as Born effective charges in the OUTCAR file, and either way, you will get both of these quantities. Towards the end of my presentation, I leave you with a little cheat sheet. It's an overview of what we've discussed and the important takeaways maybe for you to do these kind of calculations. So to compute the interatomic force constants is always the first step in phonon calculations. If you want to do these Fourier interpolations, you need to have a large supercell. But in principle, even if you do not care about the interpolation, you always want to use either the finite difference approach to calculate the force constants, or you use density functional perturbation theory. The advantage of finite differences is that it works out of the box for any density functionals, even RPA, and that is conceptually very simple and as a result also pretty stable in most cases. However, it does have the disadvantage that it will sometimes run into numerical issues with finite displacements. So you need to use more convergence tests to make sure that your calculations are correct. The DFPT driver, on the other hand, uses no such finite displacements, but it needs to be implemented explicitly for different types of density functionals. And in VASP, this functionality is restricted to only the LDA and GGA functionals currently. To activate those, you can either say iBrian equals 5 or 6. 5 means no symmetries, 6 means symmetries. In case of the DFPT calculation, you activate it with iBrian 7 and iBrian 8. I don't think I've mentioned what 7 and 8 actually do, and it is once again related to symmetry, so you would usually just use iBrian equals 8. Now to calculate the phonon dispersion in the unit cell, because remember step number 1 already writes phonon frequencies for the gamma point by just diagonalizing the dynamical matrix in the supercell. However, if you want to get the phonon frequencies at Q points that are finite throughout the entirety of the Brillouin zone, you want to set L-phone dispersion equals to true, provided that you have a large enough supercell. And in the case of polar materials, you also want to specify L-phone polar equals to true. And in addition, you specify phone dielectric and phone-borne charges. To calculate those two quantities, you can either use a finite difference approach using the PEAT method, or you use density functional perturbation theory. In the latter case, you can also use the PEAT method to compute the derivatives of the orbitals if you specify LP equals true. There is also the point to be made, I'm not sure if I mentioned this before, that again, here with the DFPT approach, you are limited to only the LDA and GGA functionals. If you use those functionals, the DFPT approach in this case can be quite advantageous. I've used it myself a lot of times, and I'm quite happy with the ease of use of the L epsilon equals true driver. If you have more complicated DFT functionals, like hybrids, for example, then you are limited to L calc eps equals to true, which also only works for systems with a gap. A little something I forget for here and there because I usually only work with gapped systems. And with this, I conclude. I would like to thank you for your attention. I hope you had some fun, and you will have some fun in the hands-on sessions tomorrow. And I would be ready to take some questions for the remaining time. Thank you very much.
Fantastic. Thank you very much for this introduction. And there are really a bunch of questions, so I would jump right into the questions, into the Q&A. So at the beginning, you explain how one finds different physical properties from looking at the perturbation with respect to internal strain, displacement, and so on. And one question is, when do we really need to take into account cross terms between strains and displacements? So the internal strain tensor, basically, where do we need that?
The internal strain tensor. That is a good question. I'm afraid I can't answer that on top of my head. It is not relevant here for phonons, not for this particular implementation. I am guessing that it will play an important role when you do methods beyond harmonic approximation.
Yeah, if I'm not mistaken, actually, I seem to recall that, but we can discuss this tomorrow, of course. But I think so. At one point, you said we look at the clamped ion response, and I think in order to get to the relaxed ion response, or the dressed response, as it is sometimes called, one would need to consider this internal strain tensor. But yeah, so it's a good idea to carefully check there. Let's jump to the next question. So on slide 17, the 4 displacements, are they in any direction or?
Ah, yes. Okay. So for n free equals 4, you mean? Yes. So this makes the displacements in the same direction, but one set of displacements is essentially the same as for n free equals 2, which means plus and minus potim. And the second set is in the same direction, but further, positive and negative. So it uses plus minus 2 times potim. And you can look up, there's a nice Wikipedia article on finite difference stencils. You can find a first order stencil that has higher accuracy, which uses 4 displacements. This is exactly the formula that is used here.
Interesting. So next question would be, why do we need to set the size of finite displacement? And going along that, so that would be slide 23, I think, where you have shown nicely how much the result could be affected by potim.
You mean this slide here?
So people are wondering about this uncertainty.
So,
well,
yes.
How much could this? What is the area that you would deem safe in this away from the DFPT line?
Yeah, safe is always, it's a good question. I mean, you see here on the right-hand side that clearly values start to diverge more and more. So here, I really do not trust these values anymore. They clearly have some contribution from higher orders. And here, this sharp decline towards 0. I mean, this here is a linear scale, right? So the closer you get to 0, the more drastic this is. But you can see this declines very fast. So yeah, the coloration here is maybe appropriate. It's more of a question, I would say, of precision. What kind of precision do you want? These are numerical methods, so choosing this parameter is up to you to some extent. VASP provides a good default. It is situated here at this point, which just lies a little bit below the DFPT result. But if you want to have the same precision, if you want this DFPT, you can try and fine-tune this parameter to lie on top of this line, but whether or not that is meaningful is another question. They are fundamentally different methods, and yeah, make sure that you are in some kind of plateau region, I would say.
And perhaps this also changes based on the external pressure that is applied. Some people may have some extreme conditions to the material.
Oh yes, of course. Maybe I haven't mentioned this the way I wanted to, but it is material dependent, situation dependent, which is why I raised this point. Like most people, like me, for example, I like to have default values that I use all the time, but some situations you will have a default value that will not be in this nice regime, and you want to make sure that you adapt it to your situation. Sometimes you want to have very tiny displacements, because already at a larger displacements, you run into some kind of anharmonicities.
So could I check that on a smaller unit cell or a smaller supercell, and then for the large supercell that I'm interested in, I do that with the potim value I determined on the smaller supercell?
Yes, I think so. You can, in principle, run this as a unit cell calculation and just look at the highest eigenvalue that you get from the OUTCAR. Just look at the highest frequency and look how it behaves under this. And I don't think it should change if you increase the, well, yeah, I don't think it should change. I mean, the value itself will change, of course, but this behavior, I think, will not change because it's related to how you do the finite difference. and not to how you do the interpolation.
Then in slide 25.
Good. So how can we see convergence here? Yes. Okay.
Yes.
That is a good question, and it might not be apparent here because I have put everything into one blot. There's this color coding that goes from the dark purple towards the light green as you increase the supercell size. And so if you just do one calculation, you do not know what you're looking for. You will get some result. So if you do just the 1-1-1 calculation, you will get something, you will look at it, and it might look like a phonon dispersion, but you have no real idea of whether or not it's correct. So you do the same thing in principle as you would with any other convergence test, and you start increasing the supercell size, and you look at the next result and see if it changes. If it changes, there's a very good chance that the first one was incorrect. And then you keep increasing the supercell size until hopefully it doesn't change anymore. And at this point, you can say, okay, there's no change. Maybe I'm converged. It's not the entire story because sometimes going from one supercell size to another one, especially if they have like an odd or even number of cells, can give you a little jump. So usually this is something I have observed myself. If you go 4 to 555 to 666 to 777, it can jump up and down as the even numbered cells or the even numbered supercells converge differently than the odd numbered ones. But it is structure dependent, system dependent. So make sure that you run enough tests so they reach a regime where you don't have any change anymore and the phonon dispersion. So in this plot, I agree, it might be a bit hard to see, but essentially the 444 and the 666 lines, they are on top of each other for the most part, and only very small changes can be seen in certain regions. That's why having a 444 calculation might already be reasonable, but going with the 666 gives you a higher accuracy, most likely. Yeah. I hope that answers the question.
Yes, I think that was useful details for how to see the convergence here. And let's go back to slide 26. There's another question to that.
Yes.
So here you have shown different exchange correlation functionals. And one question is, when you're also considering van der Waals forces in the calculation, how important are they? How much do they change the dispersion potentially?
Yeah, well, the answer is fully system dependent. I don't know the answer to this in general because it depends fully on the system. If you run a calculation in, I don't know, silicon, carbon, probably not. But if you run in water, ice, for example, then yes, the van der Waals interactions are very important, and it will probably change the phonon spectrum quite a bit, I would imagine. I have run one calculation such as this in the past, but it's been too long and I don't remember the details. But yes, I would imagine that for systems such as water, where van der Waals interactions are important, also they are important for phonon frequencies.
That leads us to more examples. There is a question, when do we actually do phonon calculations in general? Maybe you had one slide where you mentioned a couple of examples, like...
yes, I have it here. Yeah. So yeah, I can maybe give a few insights into some of these things. So, I mean, there's experiments where you can measure phonons directly. So when you want to compare your simulated materials against experiments, obviously, if those are phonon vibrations that are measured, you want to calculate phonons. So this pertains to spectroscopy in particular. Sound velocity is something that I've explicitly mentioned. You can measure this by just getting the slope here of your phonon branches, the acoustic phonon branches here at gamma. ZPR, so the 0-point renormalization, or in general, the renormalization of your band structure due to electron phonon interactions, is something that I've worked on for quite a long time. So here the process is that you essentially want to calculate your electronic band structure to higher precision or to higher accuracy. You want to calculate the band gap, for example. Band gap is always a quantity that people are interested in. And phonons, the interaction of the phonons with the electrons can change this band gap. And for this particular process, you need to calculate your phonon spectrum. You need to know how the phonons contribute to this process. This is a feature that will hopefully soon be made available also through VASP. But also, for example, in electrical conductivity, the phonons are usually the bad guys, because electron-phonon physics, electron-phonon scattering in conductors will usually mean that the electrons transfer some of their energy to the phonons, which means they transfer the energy to the lattice. And so the electrical conductivity will be lower if the electrons get to interact with the phonons. So there you also want to be able to calculate, well, which phonons are even able to interact with the electrons, and how does that affect your electrical conductivity, things like that.
Yes, thank you for expanding on that. So if our unit cell has a lot of atoms, so like 20 atoms, for example, do we need a much bigger supercell or smaller compared to the silicon supercell? Maybe, so we already cut on how to do a convergence study. Are there any tricks to make the convergence study cheaper? Can we, maybe you can expand on that?
I mean, this is an excellent question, one that I've asked myself a couple times during my studies. And it depends on this interpolation, of course. So once you want to do this kind of Fourier interpolation here to arbitrary Q points, your force constant matrix needs to be, well, the supercell needs to be large enough so that the force constant matrix is contained within, in a sense. And this is, once again, system dependent. There are some systems that require larger supercells. There's no real rule of thumb, I would say. But for systems that already have a rather large unit cell, experience shows that you don't need the same multiplicity in each direction. So you can get away with maybe a 2x2x2 cell. So I don't know if I have an example on top of my head. I mean, I once tried to run a perovskite calculation with this code. Perovskites already have rather large, very complex unit cells. And there you only need a 2x2x2 cell for this interpolation to work. But of course, you know, physically, this might not be the correct tool to really explain perovskites. So there's that. But yeah, for larger unit cells already, I mean, you don't even need a supercell if your supercell is the unit cell. Then you do not do a Fourier interpolation in this sense, but you just use the same Brémond zone as your large cell. So you, strictly speaking, there's nothing that keeps you from just using the unit cell as a supercell if it is large enough. If that makes sense.
Yeah, I think that was helpful. Then another question regarding particular choice of exchange correlation functional, but then I guess one could see that in more general. If we do a phonon calculation with HSE, does LREAL false or true work? So maybe you didn't have a slide on LREAL, right? So there actually true is deprecated. So the question is probably whether to use auto or false. Auto means we have a projection done in real space, and false means we have the projection done in reciprocal space. And how much would that affect my phonon calculation?
Yeah, this is a tough one to answer because it depends. LREAL auto is essentially a trick, right? It is another way to compute the projections that are needed in this projector augmented wave method. And it, instead of doing this projection in reciprocal space, it does it in real space, as you said correctly. And there is a small change to how the projectors are defined in real space. And in general, so this is, I think it is stated on the wiki, if I'm not mistaken, but it is also part of all the experience I've amassed through countless of these phonon calculations. that LREAL auto just tends to give less accurate forces. It came up in a lot of systems where I had some differences with LREAL auto, but for the most part, those weren't all too large. It's just that the speed up you get with LREAL auto is usually not worth it, in my experience, to the trade-off of accuracy. Please do your own testing. It is not like a given that if you use LREAL auto, it's suddenly all wrong. Not at all. It just means that it will usually give you some trade-off, and I personally think this trade-off is not worth it, so I would recommend against it. But yeah, I mean, from a like, in principle, you are free to do this. There is no actual limitation there or anything that makes those Phonon calculations incorrect. It's just a numerical trade-off.
And just to make the connection, so if we have less accurate forces, that translates also to less accurate force constants.
Yes, because in the code, the force constants are directly obtained from the forces. So, and the forces themselves, they are, well, at least for the most part, I think they are computed from the Hellman-Feynman theorem. So you have your orbitals, your cone-sham orbitals, and you stuff the derivative of your potential due to this lattice perturbation. You stuff that in between the orbitals, and you take this expectation value, which will give you the derivative of the potential, will give you then the force. And so
if you do ab initio calculations, of course, Phonon calculations are also possible with force fields, right?
I think so. Yeah, I think so. I haven't tried this yet, but I don't see why not. As long as you can calculate the force, it should be possible. It's the same with the RPA, where I think the force is calculated by some complicated Green's function method.
Then a question about slide 49, the aluminum nitride. You showed some discontinuities at the gamma point, and you also explained how these are actually physical. But if you could just elaborate on that again.
Right. So in a sense, these long-range contributions, they come from the long wavelength phonons. So as soon as you have something with very short wavelength, it kind of screens this electrostatic interaction and it fizzles out. But for very long wavelengths of phonons, these become very long-range behaviors, because the polarization for each pair of atoms is going to be the same for very long distances. And so the effect of this really comes into play around the gamma point, where we have the long wavelengths. And the reason why this discontinuity occurs is really because if you have a material, just imagine a material that has, I don't know, a frequency in one direction that is very high, but if you vibrate the material in an orthogonal direction, it's very low. So it can be a material that is super anisotropic. And of course, if you have something that vibrates very fast in one direction, you can expect this electrostatic effect to be qualitatively different than if you vibrate very slowly, or maybe even a whole different kind of atomic motion that happens. So if you just look at the long wavelength limit and you change the direction vector of that wave in an anisotropic medium, where changing the direction means your mode will look completely different, it also changes the correction of this long-range behavior. It changes the nature of this long-range behavior, and therefore the frequency will be completely different that you get. I don't know. I mean, this is a reiteration. I don't know if that actually answers the question. Like the physical insight here is really that the anisotropy is the reason. So the material looks different in different directions, and hence this polar behavior is different in different directions.
There's a question about how to find the number of displacements through VASP instead of PhononPy.
Yes, so
maybe you can
when you use VASP,
elaborate on the differences there. I think PhononPy has some symmetry taken into account, right? Some considerations.
Yes, internally, Phonopy uses spglib, which is a symmetry library that can determine crystal symmetry and all the things. And it can also so you can get all the space point groups that you can apply to your lattice. And it allows you to essentially reduce number of displacements that you need to make to the absolute minimum, crystallographically speaking. So sometimes you will end up with a single displacement along a high symmetry direction. And then by applying all the symmetry operations, you get back your individual three-dimensional displacements for all the atoms. And VASP does something similar, but the symmetry operations that VASP applies are different. And in general, VASP will find more of those independent displacements than Phonopy. But all of this is done internally. You have no control over it. The only control you have is by setting the number of displacements along each of these found direction vectors. So this is this n-free tag. So this is essentially exactly this. But the degree of freedoms that it finds, this is something VASP does internally. You have no control over it. And it essentially is like a heuristic symmetry code, I would say, that does this.
So of course, both strategies are basically using VASP as an underlying resource, and is if you're familiar with PhononPy, then that is a great strategy, and some of the functionalities are also directly available in VASP, right?
Yes, maybe I haven't mentioned this. So when you do a Phonopy calculation where you generate these displacements, then Phonopy generates for you OUTCAR files for the displaced structures, and you run individual VASP calculations for each of these displacements. And then in the end, you can combine them all to get the force constants. So the philosophy here is that Phonopy essentially uses VASP for individual displacements as a kind of driver, and then you can combine the results, whereas in VASP, everything is done in one big run internally where the displacements are made one after the other.
Thank you very much.